Howdy, I'm Kevin Hughes from the University of Bristol and the Heilbronn Institute for Mathematical Research. I'd like to thank the organizers for inviting me to speak about my recent work, which today will be on the Lacunary discrete spherical maximal functions. So just a quick refresher. We've seen some of the basic players in this game before, in particular the Hardy-Littlewood maximal function, which averages, say, continuous functions with compact support, or really any nice function defined on RD, by looking at each average at each point and taking the maximal average over all possible averages. And this resulting function is called the Hardy-Littlewood maximal function. It's a bounded operator on LP for LP greater than 1 and any dimension D greater than or equal to 1. So Lillian Pierce in her series showed us, an argument due to myself and Ari Israel from May of 2015, how to compare the continuous Hardy-Littlewood maximal function to a discrete version, which is defined similarly, where you start with a function on ZD, say compactly supported for ease, and you look at averages not over the whole ball, but over all the integer points inside of a ball. And again, taking the biggest such average in absolute value, you get a discrete Hardy-Littlewood maximal function. This is also a bounded operator on LP of ZD for LP greater than 1 and all dimensions at least 1. So those are the sort of bread and butter of harmonic analysts. More singular variant and the newer variant is due to Stein. It's called the spherical maximal function, where you again start with a nice function, and instead of averaging over the whole ball, you average over just the boundary of the ball, so the sphere. So again, at each point, I'll look at a sphere of radius r centered at that point, and I'll average the value of the function over this shell. And I'll take the biggest average. This gives me a new maximal function, the spherical maximal function. And Stein and Bergain showed that in 2 or more dimensions, this maximal function is a bounded operator on LP of RD when I have at least 2 dimensions, and LP, the P is greater than D over D minus 1. Moreover, this range is sharp. So we see, in comparison to the Hardy-Littlewood maximal function, this boundedness now depends on the dimension, and it's always a little bit away from 1, okay, from P equals 1. Now, Magyar introduced a discrete version of Stein's spherical maximal function, where you take a function defined on ZD and you average over the integer points on a sphere, okay? And you take the biggest average again to form the maximal function. Stein and Wainger showed that in 5 or more dimensions, this maximal function is also a bounded operator on LP of ZD as soon as P is bigger than D over D minus 2, and that this is sharp. If I decrease the dimension, say D equals 4, then this fails on any non-trivial LP space, basically any P that's finite. And this also fails in any D when as soon as P is less than or equal to D over D minus 2. So a natural question for harmonic analysts is to ask, well, what happens if I don't take the full sequence of spheres, which for us was parameterized by lambda being a natural number. So I'm looking at sums of squares equals lambda, some natural number. Because these are the only points that possibly have spheres on, only spheres that possibly have integer points on them. But we said take some very thin subsequence, say all the lambda are equal to 2 to the j or 3 to the j or something like that. In analogy with the continuous phenomena, Stein's spherical maximal function restricted to a Lacunary sequence of radii, you would think that this maximal function formed not over all possible spheres, but over the thin subset, is also bounded on LP for P greater than 1, okay, as soon as you have 5 or more dimensions. So I was thinking about this since the end of my PhD, and a couple years afterwards, I was able to get some progress by a sort of odd-looking theorem. Basically, you give me some Lacunary subsequence of the natural numbers, and I start measuring it in 2 different ways. I look at what happens for every prime P. I look at what happens to my sequence mod P, and I want there to be very few residue classes. Okay, and moreover, if there are few residue classes and this none of them are congruent to 0 mod P, then I'm going to have a good prime for my function, for my sequence. Then I have some remaining bad primes. You know, primes have to divide, a prime has to divide every number, so there's going to be a bunch of primes that don't fit this criterion of not being congruent 0. Then these bad primes, there have to be quantitatively very few of them, as measured by this Dirichlet series. Okay, and now as soon as I have some bounds for the Dirichlet series, I can show that the maximal function over this Lacunary subsequence is bounded on a range of LP spaces that depends on that Dirichlet series bound and the dimension. But this dimensional dependence beats out the one coming from Magyar-Stein-Wainger. So I should have mentioned that if you take a maximal function over some subsequence of spheres, this is always dominated by, it's always less than or equal to the Magyar-Stein-Wainger maximal function, point-wise, because it considers more averages that it takes the maximum of. And so we always know that any of these maximal functions is bounded on LP for P greater than D over D minus 2. So really trying to beat that barrier and get a bigger range of P by going below. Moreover, this bound holds in D equals 4 as soon as I consider one of the bad primes to be 2. So as a concrete example, Kaisa Matamaki at Hausdorff Institute's Enfant workshop several years ago in 2014 gave me the following suggestion. So I have some auxiliary sequence, the sequence of primorials. So I take the first J primes and their product, and then I define some sequence that will actually be my sequence of spheres, lambda sub J, where basically I just want to choose them congruent to 1 mod these primorials. So it's just slightly shifted off, but that's not always a prime. So then I just take the first prime that's congruent to 1 mod mu to the J, mu sub J. And I form that sequence, which grows quite quickly. And when I consider this maximal function, it happens to be bounded on LP of ZD for all D, 4 more dimensions, and P greater than D minus 1 over D minus 2. So that beats the Magyar-Stein-Wainger bound, which is nice. So while I was working on this problem, it turned out Jacek-Sienkiewicz was also thinking about it, and he took a different approach where he was trying to prove that it fails, the natural conjecture fails. And he succeeded in doing this. He actually showed that there exist Lacunary sequences inside the natural numbers for which the associated discrete spherical maximal function is unbounded near L1. In fact, if you give me any exponent p between 1 and d over d minus 1, there exists a Lacunary sequence for which it is unbounded. Even worse, you can adapt his argument to handle arbitrarily thin but still infinite sequences, which basically says that the folklore conjecture is radically false. Okay, but so it's done by a probabilistic method, so it didn't tell you anything about the structure of such sequences. A little bit afterwards, Cook managed to prove that there exist explicit sequences growing at least lacunarily, for which the maximal function is bounded on all OP for P greater than 1. Okay, so we have these weird 2 results that say there's some sequences for which is not bounded near L1, and then sequences that are bounded near L1. More recently, it's been shown that given any Lacunary sequence, the associated Lacunary maximal function is bounded on LP for P greater than D minus 2 over D minus 3 in 5 or more dimensions. So at the moment, we just have several theorems that say we have some positive results, some negative results. We don't really understand when it is going, if you give me just an arbitrary Lacunary sequence that you like, when is it going to be bounded and when is it not going to be bounded? Okay. So motivated by that question, I started to try investigating explicit obstructions. Okay. And I found that this actually depends on the p-adic Minkowski dimension of the sequence lambda. So when you measure that, say it's delta sub p, then you have that your associated maximal function is unbounded on LP spaces, or S in this case, whenever S is between 1 and 1 plus delta over D minus 1. Okay, so this p-adic Minkowski dimension is always a parameter between 0 and 1. Right, so 2 great examples to keep in mind in this case is a Lacunary sequence will have p-adic Minkowski, a Lacunary sequence in R would have real Minkowski dimension 0. And p-adically, it's when it has very few residue classes, mod p, p squared, p cubed, and so on. Say only logarithmically many. And, and on the other hand, a sequence that has Minkowski dimension 1 would be the whole natural numbers, all the possible averages, right? Great. So you would ask, so these are explicit obstructions, and you see this nice sort of criterion that depends on the dimension and the dimension in terms of ZD and also the p-adic Minkowski dimension. And one would ask if there are any more obstructions. Well, I conjecture that in view of Hasse's principle, there's some local to global principle that says, no, there aren't any more obstructions. Okay, so if you give me a subsequence of the natural numbers, at every finite prime, p, every place, I will calculate its Minkowski dimension, okay? And then I know that it's unbounded in a certain regime. And if I take the supremum over all of those, the conjecture is that I am bounded in the complementary regime, okay? But you have to also consider one more thing, and that is what happens at the real place. And then measuring the measuring the real Minkowski dimension, you get another parameter that you take into account, okay? So basically what I'm saying here is I have some sort of a Delic criterion on my sequence lambda that tells me exactly when the associated Lacunary discrete spherical maximal function is bounded. Yeah, that's the conjecture. So once you compare this with the Ziegler-Wainger-Wright theorem, which is for a continuous spherical maximal function and gives a complete characterization over when the sort of thinned out maximal functions are bounded. Okay, it tells you what range of p it fails to be bounded and what range of p it is bounded on. And that happens to come up, the same sort of idea of using Minkowski dimension comes up there. And that's what inspired us here. So those are some old results. Let's get to some very recent results. So we'll change the problem a bit. Instead of considering spherical averages, I'm going to consider ones that are sort of quasi-spherical. Okay, I'll replace, instead of sums of squares equals some parameter, I'm going to have sums of c powers equals some parameter. But in order to make this have integer points and everything, I take the absolute value to the c power and then the floor, because c will be some parameter greater than 1, but not an integer. Okay. Now you form the maximal function as before, and recent work of Yosevich, Langowski, Mirek, Zarek, and then myself and Konstantinos Poulias reveals that if you have a c that is greater than 1 but not an integer, there always exists some critical dimension depending on the power, such that for any sequence whose real Minkowski dimension is the most delta, there exists some integrability exponent p naught depending on the power c and the dimension d and of course the sequence lambda, for which the associated maximal function is bounded on LP of ZD for all p greater than that p naught. Now this sequence of exponents has the critical property that p naught decreases to 1 as delta decreases to 0. Okay, and so the main insight into both of these results, which the former by Yosevich, Langowski, Mirek, and Zarek is actually considering the range of c between 1 and 2, and then Konstantinos and I are considering the range of c greater than 2, is that when you study the operators, the underlying averages, you do a major arc and minor arc analysis, you employ the circle method, and there's just a single major arc. And the single major arc allows you to bring in the continuous behavior very well. Unfortunately, the error terms aren't so good, and that sort of gives you these critical limitations, but the main terms are giving you exactly what you expect in terms of the correct range that P naught should be. So just to end with a moral, I want to say is in these problems, these maximal functions, as the arithmetic of the variety becomes more complicated, say comparing the arithmetic of the parabola to the arithmetic of a circle, the associated maximal functions become more complicated as well. Great, thank you very much. Have a nice day.